Okay. All right. So, moving on to the next page here of the practice exam. Question number 6 here. We've got a house, and we're given the volume of the house in liters. And then we're told the concentration of radon gas, and notice we're given the mass number of radon there in the formula. We're given that concentration in moles per liter, so there's 2 units that we can use in conversion calculations. We want to calculate how many neutrons are present in the radon atoms inside the house. Okay, so one piece of data with 1 unit, one with 2 units, so we'll want to start with the 1,235. So 1,235 liters is the volume of the house that we're looking at. The concentration, we were given 3.42 times 10 to the minus 17th moles per liter. So put those units in a fraction. That will cancel out liters, which is what we want to focus on in this second step. So this will be moles of radon-222 in a liter of the air inside the house. So liters cancels out, right? So we've gone from volume units describing the air inside the house to moles, right? Now, moles of radon, we're trying to work our way to neutrons, and neutrons, of course, are subatomic particles. So what we want to do in the next step, we want to cancel moles of radon. So moles of radon-222. We can relate that to how many atoms are present in this sample by using Avogadro's number, or the Avogadro constant. So 1 mole is 6.022 times 10 to the 23rd atoms, right? Now, in contrast to the previous problem where we were talking about NH3, right? In that case, we wanted to say 1 mole is 6.022 times 10 to the 23rd molecules, because we were talking about a molecule. In this case, we're talking about an atom, so we can go from moles directly to atoms. Now, the last step here, right, there's one more step is what we're going to need, right? Maybe we should look at it piece by piece. We want to cancel out atoms of radon-222, and what we're looking for in our answer is neutrons. So we can relate atoms to how many neutrons are in an atom. We just need to remember some of our definitions. So the 222 we had here for radon, that's the mass number. And remember, the mass number is the number of protons plus the number of neutrons in a sample. So 222 is protons plus neutrons. If I find radon on the periodic table, which we can, it is atomic number 86. So that means there are 86 protons in every radon atom. If we take the mass number there, the 222, subtract out how many of those are protons, that will leave us with how many neutrons are in each of these atoms. And that is 136 neutrons. So this particular isotope of radon, there are 136 neutrons per atom. That would cancel out the last remaining unit there, atoms. I didn't cancel through the moles. I can do that right there. Right, so this would just give us how many neutrons there are. So we need to do all the math that we kind of laid out there in the calculation. So 1235 times 3.42 times 10 to the minus 7th times 6.022 times 10 to the 23rd times 136. Okay, now we started with a 4 significant figure number, but the concentration that we used in that second fraction there, that's only 3 significant figures. So that's a measured number as well. So our answer here should be 3 significant figures. So it's 3.459. I'm going to round that to 3.46. And don't forget your exponent, times 10 to the 22nd power. That's how many neutrons are in this particular sample. Okay, so I don't know if I mentioned this before, I don't think so, right? On an exam, good idea to put a box around your answer, and it makes it a little easier for me grading to kind of check your answer right? And then I can go back and check all your steps. In fact, this is a good place to maybe talk a little bit about grading, right? I have this listed as potentially a 10-point question, right? And I can assign a few points to each step here. So maybe you do kind of get off track somewhere along the way in this problem. If you did the first 3 steps correctly, right, there's a real opportunity here for me to say, oh yeah, that's right, that's right, that's right, right? This person maybe deserves 6 out of the 10 points instead of none. If you don't show me any of the work and then you get the wrong answer, well, then you don't get any points because there's no way for me to know that you were doing anything correctly, right? Even this right here could be worth some points if I say, oh yeah, they knew how to correctly get to the number of neutrons in an atom. So keep that in mind as you're practicing and as you take the test, is you really want to show me the work that you're doing, because that does give me an opportunity to kind of adjust to how you're solving the problems and give you the points that you might have earned. If I can't tell if you earned points or not, then I really can't give you points. Okay, number 7. So the sun has moved and I have a little bit of a shade here, but it looks like the video is still okay. So we'll try it like that. Density of quartz mineral is determined by adding 38.4 gram piece of quartz to a graduated cylinder. Okay, this is very similar to what we did in lab. We're trying to measure the density of maybe a regularly shaped solid, and we're going to do that by displacement. So we've got, first thing maybe to keep in mind is density is mass over volume. So we need the mass of the piece of quartz and then the volume of the piece of quartz. That's something important to keep in mind, is volume of quartz is what we want here, not volume of water. So we actually have one of those right off the bat. We're given the mass up here. The piece of quartz weighs 38.40 grams. Right now, the volume is something we'll have to figure out. So graduated cylinder contained 50.12 milliliters of water before we added the quartz. So 51.2 milliliters, that is the volume of just the water sample. After the quartz was submerged in the water, the volume was 65.7 milliliters. So 65.7 milliliters, that's the water plus the quartz, and I'm just going to use Q there for quartz. So water and quartz and the volume of the water, if I subtract out the volume of the water, that will give me the volume of the piece of quartz. Right? That's basically how much water it displaced when it was lowered into that graduated cylinder. So 65.7 minus 51.2 is 14.5 milliliters, right? And that would just be the piece of quartz's volume. So that's what we can plug in back here, is the volume for the piece of quartz, 14.5 milliliters. Right? And then all we have to do is divide. None of those units are going to cancel, so our units left over will be grams per milliliter. So 38.4 divided by 14.5. Right, now our volume here does limit us to 3 significant figures, so this density should be 3 significant figures. So I've got on my calculator 2.648, right, but I'm going to round that up to 2.65 for the correct significant figures here for the problem. Okay, and that's it for that problem. So there will be a problem, something like this on the test, something related to density. This is the problem where I will attach some of the points to getting the correct number of significant figures, right? I may also attach some points to having the correct units. So there is the possibility that you do this problem correctly and still lose points if you don't get the right number of sig figs, or if you fail to add your units to your answer. So that's something you should keep in mind for every problem. There just won't be specific points attached to sig figs for other problems. Okay. All right, one more problem, one more page, but we'll have to do that in one additional video here for the practice test.